So recall in the previous video that I said that every exponential function looks a little bit like this. So you've got an f of x, and you've got an a times a b to the x. So let's just put this in words. So f of x is equal to the original amount times a scale factor to the x power. So the original amount, like it entails, means it's what you start with. Every growth or decay starts somewhere. And the scale factor is what you multiply to show a percentage of growth or a percentage of decay. So again, this is all from the previous video, so if this is in your notes, you don't have to write this down again. So if it's a scale factor bigger than 1, so like 1.09 grows by 9% for every x. 1.25 grows 28% for every x, and so on and so forth. 1.78 would grow at a rate of 78%. Now, if the scale factor is between 0 and 1, then 0.9 maintains 90% of its original amount at a 10% decay rate. 0.85 has a 15% decay rate. 0.33 has a 67% decay rate. Ooh, that's huge. And 0.25 has a 75% decay rate. So you know what an original amount is, you know what a scale factor is, and I just want to bring to context that we care about x and f of x. So recall when we went back to Algebra 1 that f of x depends on x. So y, or f of x, is known as the dependent variable. Sorry about that. We have a dependent variable and an independent variable. So in a linear equation, let's say you have an hourly wage, dollars per hour. So if you work $12 per hour, you'll get $12 in hour number 1, and then a total of $24 after 2 hours of work, and then $36 after 3 hours of work, and so on and so forth. So that's what's called a constant rate of change. But in the world of exponents, as I'm sure you're aware in the shelter in place, that certain things unfortunately grow at an exponential rate. Okay? So when I say declare your variables, that's not me being the bad guy, it's me helping you understand what a word problem entails. So let's look at the first word problem. So unfortunately, I have to talk about this. So let's say originally there were 50 people who tested positive for a virus. Okay? Every day, the number of positive cases double. Okay, so it starts out with 50 people, then day 2, then the next day would be, then one day later would be 100 people, and then 200, and so on and so forth. So, with that being said, declare your variable. So what that means is there is an f of x, and there is an x. Remember, f of x depends on x. If you can look at a word problem and say y depends on x, then the if f of x depends on x, then the dependent variable depends on the independent variable. So let's read this problem again. 50 people test positive for the virus. Okay, so people is going to be part of the variable. Every day, the positive tests double. Okay, so what I'm gathering is that we care about the people and the day. Okay, so basically the number of people who test positive for the virus, number of positive cases, depends on the number of days. Okay, so we can rephrase this as the number of people with positive cases depends on how many days have passed. Okay, so now, how do I make an exponential equation out of this? So recall, I'm going to pull this back out, that every exponential function looks a little something like this. F of x is equal to an original amount times a scale factor to the x power. Okay, so f of x is our dependent variable. We have an original amount, so how many people originally tested positive for the virus? 50. And what is the scale factor if it doubles every single day? So 50 is the original amount, and then it takes 2 to the x power. So that's going to be our equation for the remainder of the questions. Okay? F of x is equal to 50 times 2 to the x power. Okay, so let's warm up. Let's say we care about how many positive cases there are after 7 days. How many positive cases are there after 7 days? So what this means is we look at our variables. So if the answer is in the question, how many cases after 7 days? Well, the 7 days gives me the x. How many cases? Ask the question, I don't know how many positive cases. So in other words, what this means is set x equal to 7, solve for f of x. So what we basically need to do is do f of 7 for 50 times 2 to the x power. So let's plug in x equals 7. So then we pull out our calculator, okay? And yes, the graphing calculator can do PEMDAS. So on the one hand, I suppose you could do 2 to the 7th, whatever that is, that's 128, and then times 50. Yeah, that'd be 6,400. Or, you know what you could do just to make it faster, just put it all there on the same line, because your calculator can do PEMDAS. 50 times 2 caret 7. No, not 2 divided by 7, 2 caret 7. So 2 to the 7th. Oh, come on, I'm getting all mixed up. Okay, 50 times 2 to the 7th power. Okay, so after 7 days, we will have 6,400 people test positive for the virus. So f of 7 is 6,400. So after 7 days, 6,400 cases of the virus. Now let's see what happens after 14 days. So that means we know x, the number of days, is 14. Solve for f of x, in other words, f of 14. So then we plug in our calculator. 50 times 2 caret 14. That's going to be 819,200. Do you see how dangerous a virus can be if it doubles every single day? So 819,200 cases. Okay, so I'm just going to let that absorb. So you guys have probably done that in junior high math. But then the next question is, how long would it take to infect 50,000 people? So let's think critically about this. Okay, so we know that 7 days infects 6,400 people. We know that 14 days infects 819,200 people. So we know that this 50,000 is going to be somewhere between 7 days and 14 days. But let's say we want to figure out the exact day. Okay, so once again, when it says how long does it take, this means set f of x equal to 50,000, solve for x. Okay, so now that we know the number of positive cases needs to be 50,000, so that means 50 times 2 to the x is equal to 50,000. Okay, so now we solve for x. We're going to divide both sides. Sorry, let me just set this up. We're going to divide both sides of the exponential equation by 50. So then we get 2 to the x is equal to, cancel out 1 0, so that'd be 5,000. I'm just going to double check with the calculator. 50,000 divided by 50 in the calculator should be 1,000. Okay. It'd be 1,000. Okay, so 2 to the x is equal to 1,000. Okay, now we're going to put all of our tools into this problem. How do we solve for an unknown exponent? We apply log to both sides. So log of 2 to the x is equal to log of 1,000. And what do we know? We can make this x fly to the front, and this becomes x log of 2 is equal to log of 1,000. Now we solve for x by dividing both sides by log of 2. And again, we'll round appropriately. So x is approximately, because now we're going to do log of 1,000 divided by log of 2. And that's going to be 9.965. So let's think about this logically. About how many days is it going to take to infect 50,000 people? About 10 days. And we can check our work by plugging in 50 times 2 to the 9th. That's going to be 25,600. But remember, it's going to double every single day. So 50 times 2 to the 10th, that's when it reaches 51,200. Do you see that doubling? 25,600 will double to 50, will increase to 51,200. That's how scary viruses can be, especially in a pandemic. Okay? I don't mean to scare you. I just wanted to show you that this does have a real life application. And in fact, I'm just going to tell you a funny story. So like, I was helping someone out with Algebra 2, and what's funny is that person ended up saying, like, Matt, when was the last time you did a logarithm? And, in the next example, it's going to be about money. And so, yeah, every once in a while, I do check my bank account, and I go, yeah, I do logarithms for that. Not everybody goes to the grocery store and does a logarithm. But after this current shelter in place, I never want to see anybody say, hey, we don't need Algebra 2 in our everyday life. So even though it's clearly, there's a lot of numbers at work, it's not going to be necessarily, it's going to double every single day. Every day is going to be different. The general idea is, I bet you that they are using logarithms to predict exponential growth and exponential decay. I bet you that they're doing a logarithm. Anyway, moving on to the second word problem. So let's keep it on a happy topic. Sorry, guys. So suppose that you put $20,000 into a savings account, and I'm being generous. Every year, your bank account gains 1% interest. Let's declare our variables, and then let's make an equation out of it. So what do I care about? Remember that I care about my f of x, and I care about my x. So the key is to look what depends on what. Well, I see something about money. Okay, I see something about money. That's and then every year. Hint: if it's related to time, time is always x. Time is always independent because everything depends on time. So the amount of money that you invest. So the amount of money in the account measured in dollars. So the amount of money in the account measured in dollars depends on the number of years it's been since you invested. And let's say, this is just hypothetical, let's just say you do absolutely nothing. All right, let's make an equation out of this. So f of x, it has an original amount. What's the original amount? $20,000. And you're going to gain what? So go back to our go back to our sales tax and coupons review. What is the scale factor if it gains 1%? The scale factor needs to be bigger than 1. So in particular, 1 plus 1% is a decimal, so that'd be 1.01 to the x power. So that's going to be the equation that's going to help us out for the remainder of this video. So now that we know that the money in your account depends on a number of years, we make an equation based on this information, 20,000 times 1.01 to the x power. How much money do you have in your account after 1 year? How much money do you have in your account after 3 years? How much money do you have in your account after 5 years? All these tell me, right, how much money? I don't know. How many years? Oh, I do know that. In other words, plug in for x, solve for f of x. So we could do this in 3 parts. So first things first, f of 1 tells me that if I do 20,000 times 1.01 to the x power, I'm going to do these for all 3. All right, I'm going to see if I can get some space out of this. So let's say I do f of 1. Well, that means that this is just 1.01 to the first power. In other words, this is just literally going to be 20,000 times 1.01. I don't need to take it to any power because it's just 20,000 times 1.01. So that's going to be 20,200. Notice that the 1% interest gets me an extra $200. 1% of 20,000 is 200. So that makes it grow to $20,200. Well, that's convenient. Well, what about after 3 years? So let's say I do f of 3 is equal to 20,000 times 1.01 to the third power. So I suppose I could do this times 1.01 times 1.01. I'm just trying to get you comfortable with the calculator. So 20,000 times 1.01 caret 3. So to the third power. After 3 years of doing absolutely nothing to my savings account, how much money would I have in my bank account? Well, that'd be $20,606.02. So 20,606.02. Okay, so then let's calculate how much money would I have after 5 years. F of 5 is equal to 20,000. Sorry, I had to get my pen all set up. 20,000 times 1.01 to the fifth power. So that'd be $21,020, and let's round to the nearest 2 decimal places. So $21,020.20. That's a lot of 20s. So that would be okay. So yeah, that's just how your bank account works. So even the, it'd be a smaller percentage than 1% for most banks, but the idea is the bank appreciates you for letting them use your money for lends and collecting interest on their, when their customers pay back their loans. But the key is to keep investing. Keep putting money in your savings account and your interest will grow. So let's just say I put a hypothetical out there. Let's say you do absolutely nothing. How long does it take to get at least $30,000? Okay, so if I want to figure out how long does it take to get to at least $30,000, that means that I set f of x equal to 30,000, solve for x, because I know what the amount of money in the account is. I just need to figure out what the number of years it takes. So let's say I do absolutely nothing. As you can see, after 1 year, it went from 20,000 to 20,200, and after 3 years, it went to $20,606.02. And so it's growing, but again, 1% interest is not that much. So just to show you, let's say we do 20,000 times 1.01 to the x power is equal to 30,000. So let's say I want to solve for x. Well, first things first, that x is an exponent, but luckily I can divide 20,000 on both sides. So what that does now is it leaves me with 1.01 to the x power, and I'm just going to cancel out a bunch of zeros. 30,000 divided by 20,000, that is 1.5. Now what do I do to solve for x? I'm going to log both sides of the equation, because that log allows this exponent to fly to the front. So log of 1.01 to the x power is equal to log of 1.5. So what that does is that makes this x fly to the front using the power factor rule. X log of 1.01 is equal to the log of 1.5. I'm going to divide both sides of the equation by log of 1.01. And now that cancels out, leaving me with x is approximately, well, let's figure this out. Log of 1.5, let me just clear everything. Log of 1.5, close the parentheses, divided by log of 1.01, and that gets me 40.748. So now, blah, 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 blah. But the idea is, let's say you do absolutely nothing at 1% interest and you have $20,000. How long does it take to get to $30,000? About 41 years, apparently. So what's your big takeaway from this? Put money aside in the savings account and let that interest grow. Save your money. Okay? All right, I'm going to cut it off right there. This is a good introduction to exponential functions. We're going to be doing exponential decay in the next video. Okay, have a good one.